So what you get is something like this. So you have this, let's say 2t1 over t sine omega t1 over omega t1. Okay, so instead of having the 0 points at integer multiples of pi, you now have the 0 points at integer multiples of pi over t1. Okay, so your peak value is 2t1 over t. And you have a sinc function like this. Okay. Okay. So like I said, the AK that we get is like sampling at point 2 pi over t k. Okay. So, you know, how fast you sample the signal depends on how large you choose this capital T. Okay. So in this first example here, right? In this first example here, this is the example for t equal to 4t1. Okay, t equal to 4t1. So if you plug this in, right? So in this case, you sample at pi over 2t1 k. Okay, so this is pi over t1. So you sample here, 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 and here, right? So you sample at these points, okay, and so on and so forth. And you can see that this is exactly what you get, right? So this is A0, A1, this is A2, A3, A4, and so on and so forth. Okay. Now, down here, you have t equal to 8t1. Okay. So which means that you're sampling at, let's say, pi over 4t1. Okay. K. Right. So this means that to get at the point pi over t1, right, to get at the point pi over t1, k is already 4. Okay, so for k equal to 1, you sample here, k equal to 2, k equals to 3, 4, 5, 6, 7, 8, 9, 10, and so on. Okay, and you can see that this is, indeed what we get by sampling at the purple points. Right, so this is A0, 1, 2, 3, 4 to 0, right? A0, A1, 2, 3, 4 to 0, okay, and so on and so forth, right? So as you increase this capital T, right? So as you increase this capital T, you're increasing the separation of these square waves, right? You're increasing the separation of these square waves. So as you increase the separation of these square waves, you get, denser and denser samples of this sinc function. Okay. So furthermore, down here, you have the case of t equal to 16t1, right? In which case you sample at pi over 8t1 k. Okay. And you will get 2 times the density of samples compared to this case. Okay. So you get something that looks more and more alike, more and more like the actual continuous time sinc function. Okay. So, this may not be so clear at this point, but this concept will be used in the next chapter to show how you can extend the Fourier series expression to aperiodic signals. Okay. So as you extend to aperiodic signals, okay, if you, let's say, just want to find the Fourier series representation of a square wave instead of a periodic square wave, then it's essentially the same as choosing a periodic square wave with period capital T that goes to infinity. Okay, so as capital T goes to infinity, you're essentially sampling the sinc function infinitely with infinite density. Okay, so this I just wanted to go through this example here. But later on in the next chapter, you'll see why this concept will become useful. Okay. All right, so do we have any questions up to this point?对，林玉成在吗？
在。喂。
OK，所以有没有什么问题？
到目前还好。
OK，所以这个部分主要就是在看说，如果说给你一个讯号 x of t，然后我跟你说它存在一个 Fourier series representation 的话，怎么样去找它的这些 linear combining 的 coefficient，right？那所以说我如果给你这 x of t，我要怎么样去找这个 ak 呢？所以那个玉成，如果说我给你一个 x of t 的话，我要怎么样去找这个 ak？
找 AK 的话，就是像刚后面讲的，就是可以先看零的地方，然后，喂，有声音吗？
你说什么？可以再说一次吗？
用那个，就是用那个 inner product，然后算它的平均。
所以这个 inner product 会是怎么样一个形式？
积分，就是原本的函数跟那个Fourier series 的那个 sin 跟 cosine 去做 inner product。
它的 complex exponential
complex exponential 的话就是积分在那个 interval 里面 x of t 跟 exponential 的负jk omega not t 去积分。
对 ，OK， 好，谢谢。OK， 所以就是要去找这个 coefficient 的话，就比如说我要去找第 n 项的 coefficient，我就要去取 1 over t integral over 1 period x of t 乘上我要找的那个 complex exponential 的 complex conjugate。OK， 所以这里大家可能很容易 miss 掉，就是说我如果是要去找 e to the jk omega not t 的所对应的这个 coefficient 的话，我乘上 x of t 的应该要是这个 complex exponential 的 complex conjugate。OK， 我不是直接乘上这个，而是要乘上它的 complex conjugate， 就是说要在复数这边前面乘上一个负号。OK， 所以这个是大家容易miss 掉的地方。Okay. Right. So up to this point, we have shown how to find the Fourier series representation for a signal, for a periodic signal, if it exists. Okay. Now, okay. So if you have a set of harmonically related complex exponentials, then you can construct a really large set of signals x of t that you can write in terms of this Fourier series representation. But the question is, if you are given some arbitrary periodic signal, okay, does a Fourier series representation exist? Okay. So if you are given these harmonically related complex exponentials, then by taking different linear combinations, you can construct many, many different signals. But this does not mean that any periodic signal can be written in this expression. Okay. So what we need to further, analyze or discuss is, the validity of this Fourier series representation for arbitrary signals, right? For example, this periodic square waves that we just gave in the previous example. So to discuss the validity of this Fourier series representation for arbitrary periodic signals x of t, let us start out by taking the approximation that is equal to the summation of this Fourier series only over a finite number of terms. Let's say capital N terms. Okay, so you can refer to this as the truncated Fourier series, right? We just truncate it to, capital N. So we denote this by x sub capital N of t. Okay, so suppose we take this x sub capital N of t as an approximation of this periodic signal x of t. Okay. So then we can define the approximation error, okay, the approximation error as the difference between the actual signal x of t and this approximation x sub n of t. Okay. And we can define the energy of the error, right, over one period as the integral, okay, as the integral of the absolute square of this approximation error. Okay, so again, to examine the validity of Fourier series representation for general periodic signals, we start out by taking a truncated Fourier series x of n of t, okay, as an approximation of x of t. And then we can define the error of these two, of the error as the difference between the actual signal and this truncated series x of n of t. So if there exists a Fourier series representation for x of t, then you expect that as capital N goes to infinity, the difference should go to 0. Okay? So you hope that as capital N goes to infinity, x of n of t becomes more and more like x of t and eventually becomes the same. Okay. Now, how do you, specify, what does it mean, right, for these two signals to be the same, right? How do you quantify two signals being the same? Okay, so one way to do this is by examining whether the energy of the error goes to 0 as capital N goes to infinity. Okay? Now, we are not going to go through the mathematical sophistication of proving these results, okay? But we're just going to state the results here. Okay. Now suppose that you use this energy of the error to measure how close two signals x of t and x of n of t are. Okay. Now for finite capital N, you can show, right, actually this is in problem 3.66, that the energy in the error is minimized if you choose AK according to this formula here. Okay? And in fact, if you choose AK according to this formula here, what you get is exactly the Fourier series coefficient. So what this says is that even for n that is finite, right, if you want to find a truncated Fourier series representation that best approximates x of t in terms of minimizing the energy of the error, then the best choice is to choose AK as the Fourier coefficient. Okay? So this is actually not hard to prove. I'm going to give this in the homework. But essentially how you prove this is that you just plug this expression into this E capital N, right? So you just plug this expression into E capital N. So E capital N will be a function of these linear combining coefficients, okay? So suppose that, this is E capital N and this is AK, right? So this would be a quadratic function that looks something like this. So if you want to find AK that minimizes En, what you do is that you take the value of AK, let's call it AK star, such that at this point the derivative of En with respect to AK is equal to 0. Okay? So to find this point, you take the derivative of En with respect to AK and set it to 0. Okay? So if you do that, you'll be able to find that AK should be the Fourier series coefficient. Okay? So this is something you can do in the homework. Right. Okay, but the point I want to mention here is that, if you want to find a truncated Fourier series to approximate the signal x of t, then the choice of linear coefficients that minimizes the error energy would be the Fourier series coefficient. Okay? So then if you can show that if this energy of the error approaches zero as capital N goes to infinity, then there would exist a Fourier series representation for this periodic signal x of t. Okay, so when does a periodic signal x of t have a Fourier series representation? Okay, in fact, every continuous periodic signal for which energy En goes to zero as n goes to infinity has a Fourier series representation. Okay, so it has a Fourier series representation in the sense that the Fourier series representation has an error, okay, has an error with the actual signal x of t that goes to zero, okay, in energy. Okay, so if you have, some sufficient mathematical background, okay, this is essentially saying that x sub n of t converges to x of t in L2. Right? So this is L2 convergence. Okay. But this is just for those that maybe have some background in real analysis. It's not necessary to know this. Okay, but this is just one type of convergence to claim that Fourier series representation exists for this periodic signal x of t. Okay. Now, when would this be true? Right. So without proving, so actually, one can show that all periodic signals with finite energy over a single period, okay, namely, if this is true, has a error energy that goes to zero as capital N goes to infinity. Okay, so this is true for all periodic signals with finite energy over a single period. Okay, so if you're looking at the convergence in the sense that the error energy goes to zero, okay, for these two signals, then you can say that the Fourier series representation exists, okay, for all periodic signals with finite energy over a single period, right? So this, already includes almost all signals that we would be interested in. Okay. Now, I just want to note here that this convergence does not imply that x of t does not imply that x sub n of t converges to x of t for all t. Okay, so this is a little bit different. This is only saying that the energy of the difference is zero, right, as capital N goes to infinity. Okay, so in fact, there could be certain points within this summation such that the value deviates from x of t. But those points would not matter when you take the integration because the area over those points is 0. Okay? So this is more mathematically involved, but from an engineering perspective, this is probably not as important to us because what really matters in the physical system is how systems respond to the energy of signals. Okay, so if you have these, these typical cases where you have, certain points that have that deviate in value but have 0 energy, then that probably would not matter to us in practice. Okay. Okay. So this is one way of claiming whether or not a Fourier series representation exists for a periodic signal x of t. Okay, and this existence is in the sense of the so-called L2 convergence. Right. Now we can also look at this convergence in the sense of so-called convergence almost everywhere.